So this is a very fast intro to logarithms, just to get us going with this concept. So we begin by thinking about our exponential equations we've had before. We know how to solve 2 to the x equals 8. Basically, we get both sides to have the same base. And I know that 8 is 2 to the third. And because of the one-to-one property that we have as yet to really go into, that tells me that the exponents are equal and gives me that x is equal to 3. But what if we were given 2 to the x equals 7? How would we solve that analytically? We can, of course, graph both sides of that as functions and see where they intersect to get a decimal approximation. But what's the exact process for solving this? Many students might look at this and think, well, just like when I have x squared equals something, I'll just take the root, the square root. So in this case, I will just take the xth root of both sides. However, that doesn't actually get me any closer to finding out what the value of x is. It's still just sort of stuck there basically in the exponent, because I would also write that as 2 equals 7 to the 1 divided by x, knowing my properties of exponents and radicals. So we need a process that will actually undo variable exponents, and radicals don't help us here. And you may have thought about logarithms. You may have heard of those before, but what really are they? And how do we develop them? Where do they come from? Well, to really get that idea down, we would need to understand something called inverse functions. And this comes from investigating something called abstract algebra, modern algebra, specifically group theory. And all of this was first created by Niels Henrik Abel in the 1800s. He was a Norwegian mathematician, died extremely young. It's very sad because he was very brilliant, but died of tuberculosis. Some takeaways, some main takeaways though from the work with inverses, if we were to go into it, is that inverse functions have graphs that are reflections of each other over the line y equals x. And that comes about from the fact that you kind of flip-flop the points. All of the ordered pairs, you switch the x and y coordinates. So if xy is a point on the original function f, then yx is a point on the inverse function of f. And we write that as f with a little -1 as if it's an exponent, but we pronounce it as f inverse. We absolutely never, ever pronounce it as f to the -1. You can say the inverse of f or f inverse. And basically what this says here is that inverses undo each other. So if I take off from these ideas right here and look at the function 2 to the x, where we already know some of the points on this graph. We know that this graph goes through 0, 1. 2 to the 0 is 1. We know that it goes through the point 1, 2. 2 to the first power is 2. It also goes through 2, 4. 2 to the second power is 4. Another point over here, of course, is 3, 8. 2 to the third power is 8. Back over here, we know some points as well. I'll just do this one, -1, 1/2, because 2 to the negative first power really means take the reciprocal by definition. The other thing to notice here is that this graph has a horizontal asymptote. Has a horizontal asymptote of y equals 0. We know that about this graph. Sorry, just having to manipulate here a little bit. It's not quite as easy. So we have that horizontal asymptote of y equals 0. So now I'm going to go and draw in the line y equals x. Take me a little bit here to get that lined up. the line y equals x. A little bit off on the ends here of the graph. It's not as easy. I can't just place this like you guys can with the straight edge, but all right, pretty close there. Pretty close, maybe just a smidgen over, a little bit there. So we have that graph, and now we're going to reflect this graph over that line. We're going to reflect this graph over that line. Or another way of thinking about this is I'm going to switch all of the points that I have. I'm going to switch the XY pairs of all of the points. So instead of 0, 1, I'm going to have 1, 0. Instead of 1, 2, I'm going to have the point 2, 1. I'm going to have the point 4, 2, and the point 8, 3. I've literally just flipped all of those, but notice how that gives me a reflection across the line y equals x when I do that. So reminding us ourselves here, this is the line y equals x. Continuing back a ways here, it also means that it go through 1/2, -1. The next point over here was -2, 1/4. So now I go 1/4, -2, and 1/8, -3. And the other aspect of this that we now see is that whereas this graph, the original 2 to the x graph, had a horizontal asymptote of y equals 0, we are now getting a vertical asymptote of x equals 0. So with inverses, asymptotes also switch, because if something said y equals, but you're flipping x and y, then it now becomes x equals. So we have now this as our vertical asymptote, x equals 0. Might make more sense to put it down here where it's actually becoming asymptotic, equals 0. And now I am ready to go in here and draw the graph, which on this tablet is going to be extremely difficult to draw very well. Forgive my drawing here. You guys, of course, know that your drawing should be a lot better. And then we come in here and remember that exponential functions approach their asymptote really quickly. And that is also true here of log functions. They approach their asymptote really, really quickly. In other words, for very small amounts of x above x equals 0, you're really, really close to that vertical asymptote. So this is the graph of the inverse here. And so we know it exists here. If we understand inverses, this graph truly exists, and we just have to give it a name. Basically, we just have to call it something, because as you will see with a study of inverses, there is no algebraic way to find the inverse of this, because 2 to the x is a transcendental function, meaning not algebraic. So its inverse is also not algebraic, cannot be found with algebraic means. So remember, we denote that with f inverse, and f inverse of x is going to be named log base 2 of x. So just by definition, we take the inverse of 2 to the x, and that creates a function we call log base 2 of x. We can do this with any base that we want. So remembering the function f of x equals e to the x, which went through 0, 1, of course, like all exponential functions, and goes through 1e and 2e squared, -1, 1 divided by e. So doing exactly the same thing as the 2 to the x graph, although those numbers are a little different. E is about 2.7, e squared is about 7.4, and 1 divided by e is pretty close to 1/3. Again, we have a horizontal asymptote on this graph. So that is going to create a vertical asymptote on my inverse function. We'll move that over just slightly to get it more on that axis there. All right, right there. And we come in here and we flip-flop all of the points. So instead of 0, 1, I again get 1, 0. Instead of 1e, I get e. It's about 2.7, comma 1. I get e squared 2. E squared is about 7.4, 2. And I get 1 divided by e, which is about a third, negative 1. I'd get 1 divided by e squared, which is about a seventh, and negative 2, for example. And there is the inverse of the e to the x graph. Thank you for your patience with my drawing here. So here's my inverse. And it again also gets really close to the x-axis pretty quickly. In fact, even more quickly than the 2 to the x graph. Although I'm really having a difficult time drawing this on this pad. Sorry about that. All right, we're gonna have to just go with that there. All right, make sure you're doing a much better job. So this goes through e squared, comma 2. This goes through e, 1, 1, 0, and 1 divided by e, negative 1. So something that is important for us to sort of see here as far as what's happening with this is that e squared, the output I get is 2. And e to the first, the output I get is 1. And 1, which can also be written as e to the 0, the output I get is 0. So the log function is basically always telling us what was the exponent. That's the output of the log function. Well, just a note here that every exponential function of a certain base has a corresponding inverse function, or in other words, a logarithmic function. We usually abbreviate that and just say log. Has a logarithmic function with that base. So we just saw that if we have f of x equals 2 to the x, then its inverse is the function log base 2 of x. The base is very important, just like the base on the exponential is important to say exactly which graph you're talking about. Right here, if I have 5 to the x, its inverse is log base 5 of x. If I have e to the x, just like I did, I forgot to write its name down, but we can do that here now. I would get log base e of x. Technically speaking, there are parentheses here, so it's of x is how you pronounce it, log base 5 of x, log base b of x, but almost no one writes those parentheses unless there's addition or subtraction inside. One other very important note here, the base e log function is extremely important in calculus. We've already discussed how Euler's number is a really important number that shows up over and over again in calculus. And because of that, mathematicians like to really abbreviate this and make it much shorter. So we write LN. And that stands from the French for logarithmique naturel. So log natural, because in French, like Spanish, you reverse the noun and the adjective. So that's where that comes from, but it definitely means base E, sorry. So it's natural log of x is how we pronounce that. The natural log of x is how we say that in English. Natural log of x. All right. Well, not only do the exponentials have a corresponding log, but all of the logs have a corresponding exponential that are their inverses. So if q of x equals log base 3 of x, then the inverse of q is the 3 to the x exponential function. And if r of x equals log of x, now that's a curious thing there. There's no base on it. Well, it turns out that for science, the base that makes the most sense to work with is base 10. And in a way, in order to be efficient with that, because that's pretty much the only base that science would use, they decided to not have to write the base every time, but it means base 10. So the inverse function of log x, or in other words, log base 10 of x, is 10 to the x. So mathematicians have their favorite right here, the log base e function called the natural log, and scientists have their favorite one, which is the log base 10 function, and we simply leave off the base and understand that it's there. Both of these are written with shorthand that makes it a lot faster for those two fields. So looking at this and kind of remembering what happened over here with the input and outputs flipping, and looking again here about the fact that each of these has a corresponding inverse function, we want to rewrite the log equation we have here as an exponential equation. And basically what that means is that this is your exponent and this is your base. And so the corresponding exponential equation, and by the way, this is an if and only if, which in math we write with a double barred arrow. So if this is true, then this is true. If this is true, then that's true. So the corresponding exponential equation is 5 squared is equal to 25. So log base 5 of 25 is equal to 2 because 5 squared is 25. Now, what if we had an exponential equation and we want to write it as a log equation? Well, I know that 9 to the 1/2 really means the square root of 9, and the square root of 9 is 3. So here's the exponential equation that I have. And now the implied log equation from this is log base. Well, the base was 9. The output was 3, but that now becomes the input of the log function. And the input of the exponential was 1/2, but that becomes the output of the log function. So again, what we're seeing here, the really, really big concept is that logs equal the exponent on that base. Logs equal the exponent that went on that base to give this input number. And so the way that I like to think of it is logs simply ask, what was the exponent? And if we use that idea, then we can evaluate logarithmic expressions. So what was the exponent? What was the exponent I put on the base 9 in order to get 3? Oh, 9 to the 1/2, meaning the square root of 9, is what gives me a 3. So we're going to evaluate the following logarithmic expressions, and we want to do this without a calculator, and we want exact answers, not decimal approximations in any case. So if I have log base 3 of 9, so I'm kind of flipping what I had on the other page, if I want to know what does log base 3 of 9 equal, I could, in my mind, I could come in here and think, okay, well, what's the corresponding exponential equation that goes with that? And it's, well, 3 to the question mark is equal to 9. That's what I'm thinking. But again, if I simply say it, I just ask myself, what exponent do I put on the base 3 in order to get 9? And clearly that has to be 2. The exponent that I would put on 3 to get 9 is 2. Logs simply ask, what was the exponent? So looking right here, log base 5 of the square root of 5, well, the square root of 5 is what power of 5? So again, coming in here, I could kind of try to turn this back into an exponential equation to think about it. It says 5 to the question mark equals the square root of 5, but I know square root of 5 is 5 to the 1/2. So what exponent would I put on 5 to get the square root of 5? I would put 1/2. So this is how logarithms work. And at least to begin with, this is pretty much how simple they are. They're really not as much of a mystery as we would imagine. Another way to go about this is to just go ahead and rewrite the input as a power of the base. So I know in this case, for example, that 1 divided by the square root of 7 really means 7. The reciprocal means a negative, and the square root means a half. So what exponent would I put on 7 to get 7 to the exponent of negative 1/2? It's negative 1/2. What exponent do I put on 7 to get 1 divided by the square root of 7? I need a negative in order to take the reciprocal. I need a half in order to do the square root. This one might be a little bit trickier. Log base 5/4 of the square root of 64 125ths. But if I recognize, of course, that 64 is 4 to the third power, and 125 is 5 to the third power, and then I have a square root on it, which means a 1/2 power, but I also have this fraction flipped over from what I originally did. If I'm super clever and can think about that all in my head together, I can simply write that this is equal to negative, because of the reciprocal, because of the flipping, 3/2. 3, because that's the power that goes on each of those parts of the fraction, and half because I put a square root on it. Again, you can try to take your time and go through writing an exponential expression like we did here, especially working through it like we did in this case. But eventually you want to be able to just look at that and just ask yourself, what exponent did I put on this base to make this expression happen, to make this input happen? Well, some expressions, in fact, most expressions, are not quite as easy to figure out, but you can at least sort of get an estimate of their value. So for example, what if I were asked to determine log base 3 of 11, but to just figure out what two integers it's between? And so you think about nice powers of 3 that are near 11. The first one that I think of is 9, and log base 3 of 9, what exponent would I put on 3 to get a 9? Is 2. The next nice power of 3 is 27. So what exponent do I put on 3 to get 27? I get a 3. So if log base 3 of 9 is 2, and log base 3 of 27 is 3, then hopefully it's fairly clear there that log base 3 of 11 has to be between 2 and 3. And in fact, probably a lot closer to 2 than it is to 3. So with this, we're just trying to make sure that we understand logs enough that we can roughly estimate the value of logarithms that don't come out so nice and perfectly. In this case, a little bit trickier. I'm talking about reciprocals, so I need to think about powers of 2 that give me reciprocals. And I might think about 1 divided by 16, which is negative 4. Another one then that is past 1/25th is 1/32. So log base 2 of 1/32 is negative 5. Negative because of the reciprocal, 5 because 32 is the 5th power of 2. So 1/125th is definitely between 1/16th and 1/32. So I can say that log base 2 of 1/25th is between negative 5 and negative 4. Again, this is just getting us some familiarity with these values even when they're not nice numbers. And then finally, the logarithms have properties, and each of these correspond to properties of exponents. And for the purposes of this, m and n have to be positive, because one of the things that turns out to be true about logarithms is that the domain of any log function prior to any transformations is 0 to infinity. And again, because of that flip-flopping of x and y, the range of my original function, which is y, becomes the domain of my inverse function, because that becomes x. So the domain of the log function is 0 to infinity. And that's true for all log functions before you do any transformations. Remember, we call this one the natural log function, and the domain here is, as you can clearly see from that graph, that domain is all of these numbers here past 0, but not including 0 itself. You can never hit that asymptote, and so the domain is 0 to infinity. So because of that, I need to be careful with my properties that I'm speaking strictly about positive inputs. And we know that the base of an exponential function must be positive and not 1. So that is also true of log functions. The base of a log function must be positive, but not equal to 1. So here's our first property. Log base b of m times n is equal to log base b of m plus log base b of n. Again, there are some hidden parentheses. As long as it's multiplication, we tend not to put it, but we are talking about the log of the whole quantity, m times n. That's a product. If we think back to exponents, remember that with exponential properties, if you have two powers multiplied together with the same base, you add the powers, you add the exponents. Well, logs are exponents. So that's kind of the way you can think about this. When you have multiplication, you add the exponents, because each of these logarithms represents an exponent. And I like to say this just a little more. I'd start getting these chants that help me remember them. So the log of a product is the sum of the logs. Notice I didn't say the logs of a product is the sum of the log. So the S or the not S here is pretty critical. The log of a product is the sum of the logs. So the log of a product is the sum of the logs. That's how I remember that. But again, it goes back to exponents. What do you do when you're multiplying with exponents? You add the exponents. Similarly, what do you do when you're dividing with exponents? You subtract the exponents. So the log of a quotient is the difference of the logs. The log of a quotient is the difference of the logs. And then what if I raise m to a power? And this one is very, very, very important to understand where the parentheses are implied here. Exponents happen first, so the implication is that m is raised to the k, and then you're going to take log base b of that quantity. So what happens when you raise something to a power with exponent rules? You multiply the exponents together. And so we get that the log of something to a power is the power times the log. That one you got to kind of run through a little quicker to make it fit the chant nicely. The log of something to a power is the power times the log. In this case, though, k can be any real number, because as we already saw over here, the log can actually equal a negative number. And if I were actually writing this a little differently, this really means log base 2 of 2 to the negative 4. So exponents inside of logs can be negative. It's just that the expression itself has to be positive. So the log of a product is the sum of the logs. The log of a quotient is the difference of the logs. The log of something to a power is the power times the log. When you then combine those along with the idea of inverses, the idea of flip-flopping inputs and outputs, You get some other things that you should just recognize and be able to work with instantly and not even have to use your properties of logarithms to figure them out. The first one is that log base b of 1, regardless of the base, has to be 0, because we know that the base to the 0 power equals 1, and we're flip-flopping the inputs and outputs. So if the input of log is 1, that was the output of the exponential function, which came from using the exponent of 0, so that's the output of my log. In a similar way, log base b of b, no matter what the base is 1. Log base 17 of 17 is 1. What exponent would I put on 17 to get 17? I would put the exponent 1. Log base b of the reciprocal of b is a -1. And then this is the really important one for us going forward after this lesson here, is about the inverse nature of these two functions. It turns out that log base b of b to the x is equal to x. It's kind of what we're seeing up here in a little bit, but it extends and applies for any x. And again, in this case, x can be a negative number as well, so this applies for all real numbers of x. In a similar way, b raised to the log base b of x equals x. And this is that idea that I mentioned earlier about inverses, that they undo each other. They undo each other. I put x into an exponential function, then I took that and put it into a log function. I just got back the x I started with. The log undid the exponent. The exponent undid the log. In this case, though, you have to start with an x that's positive, because you can only put positive numbers into log. And one final property that you've probably heard of, called the change of base theorem, is that if you don't like the base of the logarithm you're working with, for example, some calculators only have base e and base 10 on them. So the only way to calculate something like log base 5 is to change the base into a different base that you like. And the way it works out, don't have time to prove it here, but the way that works out is that log base b of x, you can change it to log base a of x as long as you divide by log base a of the old base b. So for example, I could calculate log base 5 of x by instead doing the natural log of x and dividing that by the natural log of 5. And this gives us a way to evaluate logarithms on calculators that do not have anything except log base 10 and log base e.